Hello, welcome back to the second course in physics, and we are still discussing the topics of electrostatics, and in this lecture I will be talking about the concept of electric potential. The contents of this lecture will be as follows. First of all, we'll be discussing the electrostatic potential energy, and from which we can derive the concept of potential, electrical potential. Then the relation between the electric potential and the electric field is derived. And as an application, we will discuss the electric dipole problem, and we will discuss the equipotential surfaces. Then we will set up a Poisson equation, Laplace's equation, and we will touch on some applications of these. We know that the concept of potential energy is related to work done on systems, where if an external force does work on a system, this work can be saved in the system in the form of potential energy. And consequently, if a force, a conservative force, acts on a particle as it moves in the field, some displacement, this conservative force does work, and that work is stored in the system in the form of a difference in the potential energy of the system, and that potential energy is given by the formula derived in during the discussion of the first physics course. The difference in the potential energy is given by negative the work of the external force, external conservative force, du equals minus f dot dl, where dl is the displacement that the particle moves under the influence of the force F. And so if a test charge moves from a point A to a point B in the presence of an electric field, then the difference in potential energy, delta U, is equal to the potential energy of the system in the final state, U sub B, minus the energy, the potential energy of the system in the initial state, and that is by definition equals to the integration from the initial configuration A to the final configuration B of minus F dot dl. In this case, F is equal to Q naught, which is the test charge, times the electric field. That is the force. So that's simply minus F dot dl integrated over the displacement from point A, from the initial configuration to the final configuration. And in the case if we have, for example, a point charge, the point charge sets up a field in the region around it. So if the test charge Q moves from point A to point B, we track it, we consider dl at every point, and we calculate the electric field set up by the point charge Q, and then we can evaluate the difference in potential energy from this configuration. This concept of electrostatic energy is linked with another concept which is the electrostatic potential. This quantity, this physical quantity, the electrostatic potential, is derived from the electrostatic energy actually, and is defined as the difference in potential as the point charge moves in the field, a displacement dl is equal to the difference in potential energy introduced to the system divided by the charge q naught, the test charge, which is simply equal to minus E, the electric field that is applied to the point charge q naught, dot dl. So minus E dot dl is the difference in potential, in electrostatic potential, as the point charge moves a displacement dl in the field. Thus, we can calculate the electrostatic potential from the difference between initial configuration and final configuration. So the potential difference delta V for a system, if it moves from configuration A to configuration B, from state A to state B, is simply the potential in B, in state B, minus the potential in state A. And that is, from the upper definition, is the integral from A to B, from the initial state to the final state, of minus E dot dl. That integral gives us the definition of the difference in potential between two states of the system as a charge, for example, or a collection of charges move for the system. And the units now involved in these definitions are as follows. The unit of the potential is simply joule per coulomb, because it's energy divided by charge. And this unit is called volt, after the scientist Volta, the important scientist Volta in this field of electricity. And the unit of the electric field, in terms of, it can be defined in terms of the force, as force per charge, or in terms of the voltage, volt per meter. So it could be Newton per coulomb or volt per meter. The electric potential due to a point charge can be evaluated now with these definitions. So how can we do that? If we recall the electric field due to a point charge that we have mentioned and evaluated previously, the electric field of a point charge is simply Q over 4 pi epsilon naught r squared times r hat. R hat is the unit vector radially outward from the point charge. So if the point charge Q is positive, that means the electric field is radially outward as expected. And if the point charge Q is negative, then the electric field is going radially toward the point charge, which is consistent with the previous argument of the lines of forces. And thus, putting these quantities, the known quantities, then we can arrive at the formula VB minus VA. B is the final position of the charge, and A is the initial position, is equal to minus integral from A to B of the electric field Q over 4 pi epsilon naught r squared r hat dot dl. In this case, dl is simply r hat dr, because we keep the beginning of the position at the point charge, and we change that position vector. Then dl is simply r hat dr. And performing this integral, this will give Q over 4 pi epsilon naught r sub b minus Q over 4 pi epsilon naught r sub a. This is the difference, and you notice that the difference is dependent on 1 over r final and 1 over r initial. And now, if we take a reference point r sub a is equal to infinity, the initial position is at infinity, then V at A is equal to 0. If we are at an infinite distance from a point charge, the effect of that point charge is 0 at an infinite point. So if we set RA equals to infinity, then V sub A is equal to 0, and that will give us the potential at a point R, a distance R from the point charge, which we call the point B in the previous discussion. Then V at R, which is called VB in the previous formula, is equal to simply Q over 4 pi epsilon naught R. R was R sub B in the previous formula, but we call it now R to be applicable to any point in space without any name for it. So at a point, at any point, a distance R from a point charge, the potential is simply Q over 4 pi epsilon naught R. It goes as 1 over R, and it is a scalar quantity. It doesn't have a direction. The electric potential due to a charge distribution, if we have a macroscopic charge distribution, then now we know the electric potential due to a point charge. So we divide this charge distribution conveniently into point-like charges, and we evaluate the electric potential due to each point charge, and then we add them up together. And it's a simple addition because the electric potential is conveniently a scalar quantity. So in that sense, dq is the element of charge, or point-like element of charge, and V is the summation of all the contributions of the point charges, dq over 4 pi epsilon naught R. And again, dq is calculated from the charge distribution. And this looks like, if this is the body of an arbitrary shape, we can dissect it, or we can divide it into small elements, each one of them carrying a charge dq going to 0, and R is the distance between that dq and the point of interest where we are calculating the potential. And the potential is simply the summation or the integral over the charge distribution over the source. And that was the relation between the potential and the charge distribution. Now, we have mentioned before that we can replace the charge distribution by the field, the electric field. We can deal with the problem as being due to a charge distribution or as due to a field. So in this sense, we come to the point where we need to discuss the relation or derive the relation between the electric field and the electric potential, since we can replace the distribution, charge distribution, by the concept of the electric field, as we mentioned previously. And in the integral form, we have the previously defined relation V at point R is equal to the negative of the integral from the reference point at infinity, which was A previously, from infinity to the point R, that is the final point where we are evaluating the potential, of the quantity E dot dl. That integral defines the integral relation between the electric field and the potential. This way we can derive the electric potential V sub R if we know the formula for the electric field. We can do the integration, and hopefully if it is simple enough to do the integration, we can calculate it. Now the differential form is, if we recall that the quantity minus E dot dl is simply the difference dV as we move the point charge a distance dl, and that dV can be defined in a different form. It's simply the gradient of V dot dl, where dl is the displacement. It's something like dV by dl times dl. It's something like that. So this is the difference in V, and thus E is equal to minus the gradient of V, where the gradient of V, as we have defined the gradient previously, is equal to dV by dx in the direction I hat, or in the x direction, minus dV by dy in the y direction, minus dV by dz in the z direction, or k hat. Thus, E is equal to minus gradient V. This is the differential form of the relation between the electric field and the electric potential. And now let's consider an application to the previous definitions of the electric potential due to a charge distribution. And one of the simple charge distributions and the important ones is the electric dipole. And let's consider the electric dipole problem. And for the electric dipole, the electric potential is simply the electric potential Q over 4 pi epsilon naught times 1 over R plus minus 1 over R minus. The first term is coming from the positive charge, and the second term is coming from the negative charge. So we have two charges, and we add up their contributions. And for R much greater than D, R plus is equal to R minus D over 2 cosine theta, and R minus is equal to R plus D over 2 cosine theta, where the relations between R minus, R plus, D and theta are illustrated in this figure. R plus is the distance between the positive and the positive charge and the point of interest, where we are evaluating the potential, and R minus is the position vector from the negative charge to the point of interest. And we are considering the two-dimensional plane, which is the xz plane. That's the plane we are working on. And theta is the angle. Theta is the angle between R, the position R, from the center of the dipole to the point of interest, and between the z direction. That is what theta is. And now substituting these values in the formula for the potential for the dipole, we get the formula V is equal to Q over 4 pi epsilon naught, and in parentheses 1 over R plus, which is R minus D over 2 cosine theta, minus 1 over R minus, which is R plus D over 2 cosine theta. This is the general relation, and now if we substitute these approximations and we expand the term in the parentheses, we obtain V is equal to QD times cosine theta over 4 pi epsilon naught R squared. And if we recall that cosine theta is cosine of the angle between R vector, the position vector of the point from the center of the dipole, and the z-axis, or simply P, because P, the dipole moment, is in the direction of z, as we have constructed it from going from the negative charge to the positive charge in the direction of z. That means this quantity V is equal to QD cosine theta over 4 pi epsilon naught R square can be rewritten as P vector, P quantity is QD, the magnitude of P, dot R as a vector in order to account for the cosine theta, and we have to divide by magnitude of R in order to leave the unit unchanged, over 4 pi epsilon naught R cubed, and that is in the limit of R much greater than D. That means at points farther away from the dipole. This is the potential at points far away from the dipole. It's like P dot R over 4 pi epsilon naught R cubed. And now we talk about the concept of equipotential surfaces. This is a concept that is linked with the concept of potential. From the name, equipotential surface is a surface where the potential is equal on all points of that surface. So to begin with, we mentioned that a scalar field is represented graphically by surfaces, where each surface is the locus of all points at which the scalar point function is constant, has a fixed value. This is equipotential. So the equipotential surface is thus, according to this definition, can be defined by a scalar point function, f of x and y and z. This is a function of space, is equal to v. So if we set this quantity equals to a constant, then the function f of x and y and z defining the surface defines a surface with constant value. If that value is set to the value of the potential at that surface, then this constructs the equipotential surface, and it would describe the shape of the surface. The definition of the equipotential surface dictates that if we change the position of a point from one point to another on the equipotential surface, then the change in the function that describes that surface is equal to 0, which is equivalent to saying that the difference between the potential on two different points on the equipotential surface is equal to 0, because the potential is the same at all points on the surface. And thus, if we assume that we move from one point on the surface, if we move a vector displacement ds, a length ds, a small length ds, then the difference in the function, in the point function, df, which is defined as the gradient of f dot ds, this is the length moved along the surface, is equal to 0, because if we move from one point to another on the surface, on the equipotential surface, the change in the potential or the change in the function describing the potential is 0. So this says that gradient f dot ds is along the surface, is an arc along the surface, that is equal to 0. Since ds is not 0 and gradient f in general is not 0, that means the angle between them is 90 degrees in order to have gradient f dot ds is equal to 0, which means that this simply implies that the gradient is always normal to the surface, because gradient f and ds are normal, are at 90 degrees from one another. And this figure is a representation of the previous argument, where we move from R1 to R2, a displacement ds along the equipotential surface. The equipotential surface is represented by the line here, because we are dealing with only two-dimension, so the surface looks like a line. And the gradient is normal. It's at 90 degrees with ds. So this would give us the facility to understand or the opportunity to understand the direction of the electric field relative to the equipotential surfaces. Since we have the differential form of the relation between the electric field and the potential as E is equal to minus gradient V, and V is a scalar function depending on space, where you are on space. Since this is true, then the equipotential surface, the gradient of V is always normal to the equipotential surface. That means E, the electric field, because it's a gradient of the function that determines the potential, then the electric field is always perpendicular to the equipotential surfaces. That is a conclusion. So if we have, for example, a point charge, the point charge, the equipotential surfaces are spherical around the charge, with the point charge at the center. At those points, at each spherical surface around the point charge, the potential is exactly the same, because the points on the surface are at equal distances from the point charge. That means if we argue that the electric field should be normal to the equipotential surface, that means the electric field of a point charge should be radial. And that is the same conclusion that we have arrived at by previous argument. Now, according to this argument, we can construct the equipotential surfaces for any distribution of charges. And for simplicity, if we assume that we have a dipole, a positive charge and a negative charge with a separation between them, then the field lines are constructed as before, and the equipotential surfaces in red are the surfaces that are constructed normal or perpendicular to the field lines at all points. So constructing these surfaces will give us the shape of the equipotential surfaces, which are normal to the electric field lines. That is for the dipole. And similarly, if we have two positive charges, from a previous argument, we have constructed the electric field lines, and we can construct the surfaces that are perpendicular to these field lines, and the surfaces look like this for two similar charges. This is not restricted to positive charges. For negative charges, for two negative charges, the same thing will be observed. The same thing applies. The equipotential surfaces look similar. And now, to see the electric field and the equipotential surfaces more, and the relation between them more, we consider two successive equipotential surfaces. The first one is at potential Vi, and the second one is at potential Vi plus delta V, where delta V is the difference in potential between these two surfaces, two successive surfaces. If these two surfaces are separated by a distance delta n, and this distance is normal to the two surfaces, because that's the distance between two surfaces, simply the normal distance between them, then this figure shows these two surfaces with the distance delta n between them, and the first one is at Vi, the second one is at Vi plus delta Vi. From the definition before, the difference between the potential between the two surfaces is by definition equals to the gradient of V dot the displacement between the 2 points on the two surfaces, which is delta n times n hat. N hat is the unit vector in a direction perpendicular to the surfaces. So delta V is gradient V dot delta n in the direction normal to the surfaces, and thus delta V over delta n, if we divide delta V by delta n, both sides of the equation by delta n, we reach delta V by delta n is equal to, in magnitude, is equal to, of course, it's equal to gradient V dot n, and gradient V is always perpendicular, normal to the surface, equipotential surface. So it could be either in the direction of n hat or opposite to the direction of n hat. It's on that line. So it's going to be plus or minus the gradient, the magnitude of the gradient of V. Plus if it's in the direction of n hat, and minus if it is opposite to the direction of n hat. And thus, delta V by delta n is simply plus or minus the magnitude of the electric field. That means the electric field is perpendicular to the equipotential surface, and it could be going out if the charge is positive, and going in an opposite direction to the normal to the surface if the charge inside is negative. And the electric field is stronger if the two successive equipotential surfaces are the closest to each other. That means in regions where the equipotential surfaces are stacked closely to each other, then we see that the electric field is stronger in these regions. And as an example, the equation of the equipotential surface for a dipole, if we use the dipole approximation that we have derived a little while ago, V is equal P dot R over 4 pi epsilon naught R cube. If we set V is equal to a constant that is for an equipotential surface, then we can derive the shape of the equipotential surface for the dipole, which we have constructed a little while ago. And that shape of these surfaces is simply R is equal to the square root of P, the moment, over 4 pi epsilon naught V times cosine theta. Everything is constant except cosine theta. So this gives us a function of R as a function of theta. And this is a function of a surface in space. Of course, the equipotential surfaces are drawn as lines, but if you rotate this line in space, then you get the whole surface, because we don't have the facility to draw three-dimensional space. So we draw a line in 2 dimensions, and then you can rotate that line, and then you can get the whole surface. That's our argument. And now we can go into the differential argument of the potential, and we consider Poisson equation. Poisson equation is a formulation, actually, of the potential. How can we evaluate the potential? Through a single differential equation that applies over a region. So if we can set up a differential equation concerning the potential that applies on a certain region, and we know the boundary conditions at the boundaries surrounding that region, then we can construct the potential, and we can evaluate the potential that satisfies these boundary conditions. This is Poisson equation. From this can be obtained from the differential form of Gauss law. The differential form of Gauss law is simply div E, as we have derived before. Div E is equal to rho over epsilon naught, and div E is equal to div minus gradient V, because E is simply minus gradient V. And that gives div dot gradient is simply gradient square. And this gives minus gradient square of V is equal to rho over epsilon naught. This differential equation states the relation. It's a second order differential equation that states the relation between the potential and the charge distribution. Gradient square V, which is d2V by dx square plus d2V by dy square plus d2V by dz square, is equal to minus rho over epsilon naught, a relation between second order differential equation relating the potential with the charge distribution in space. And Laplace equation is a special case of Poisson equation, where in a certain region of space, if we have no charge distribution, if rho is equal to 0 in a given region of space, then the relation Poisson equation gives gradient square V is equal to 0, and that's Laplace equation, which is a special case of Poisson equation. And this is applicable in regions where there is no charge distribution. It's actually convenient to solve problems with no charge distribution at those locations. Now we consider some applications. And we consider the application of Laplace equation, which is a simple equation to deal with. For example, we consider two infinite parallel plates with no charge in between. We are considering the problem of evaluating the potential and the field in regions of space that do not contain charge. So we consider two parallel plates. The potential on the first is known, the potential in the second is known with no charge in between, and we are interested in evaluating the potential and the field in between these two plates. We set up the Laplace equation, gradient square v is equal to 0. But since we have no variation in the YZ plane, in the YZ direction, the only change in the problem is as we move from one plane to another, to the second plane. And that dimension, we call it x, as we move from one plate to the second plate is the dimension x, and that's where we get the changes. So setting up this, d2v by dx squared is equal to 0. The solution of this differential equation is simply v of x is equal to c1, which is a constant, plus c2 times x, that c2 is another constant, times x. And these are the plates. The boundary conditions are that the potential at the first plate is v naught, and the potential of the second plate is 0 by definition. By earthing it, we earth the second plate, and the first plate, we consider that its position is at x equals 0, and the second plate at x equals d. D is the spacing between the two plates. And thus, the boundary conditions are v of 0, v at 0, at x equals 0 is equal to v naught. V at d is equal to 0. And putting these together, we arrive at the relation v of x is equal to v naught times 1 minus x over d. That's after applying the boundary conditions. This gives the relation between the potential and the distance between the two plates, and the electric field is derived from the relation between the relation between the electric field and the potential. E sub x is equal to E, that's the only component of field, is equal to minus dv by dx, which is simply v naught over d. That is the electric field, and the electric field is known to be constant between the two plates, which is equal to v naught, the difference between the potential between them, divided by the distance between them. And now we consider Poisson equation, where there is charge distribution. So we consider the same problem as before, with a charge distribution rho filling the space between the two plates. The same plates as discussed before, but with rho filling the space between them. From Poisson equation, d2v by dx squared in this case is not 0, but rather it's minus rho over epsilon naught. Now we solve this differential equation. Solution gives v of x is equal to c naught, constant, plus c2x, c2 is another constant, minus rho x squared over 2 epsilon naught. This is the solution of the previous differential equation. And now we consider the boundary conditions at x equals 0 and at x equals d. The boundary conditions would give C1 is equal to V naught, and C2 is equal to rho d over 2 epsilon naught minus V naught over d. This is a result of the application of the boundary conditions. Thus, putting these values of the constant, undetermined constant, which we determined from the boundary conditions, putting them back into the formula for V of x, then we get V of x is equal to V naught times 1 minus x over d, close parenthesis, plus the second term is rho over 2 epsilon naught, open parenthesis, xd minus x squared. So this gives the potential between the plates at any position between the plates, and the electric field is derived from this potential, E sub x, which is the only component of E between the plates because of the symmetry in the YZ direction, is equal to minus dV by dx, which is simply V naught over D minus rho over 2 epsilon naught times, in parentheses, D minus 2x. And the first term, there are two terms. The first term, V naught over D, is ascribed to the charge on the plates as before, as in the previous example. So V naught over D is the same term that appeared in the first example without a charge distribution. Thus, the second term is due to the charge distribution. If we set rho is equal to 0, we get the previous result, where rho is equal to 0. The term due to the space charge rho between the two plates, we notice that it changes sign as we move from one plate to the other. And by this, I would like to conclude my lecture, and thank you for your listening.